Yeah, welcome all to today's talk. Today, Snehashis Mukherjee, PhD student at our department, will talk about quantum spatial aging algebra and its representations. Okay, please start.
Okay, so am I audible?
Yes, you are audible.
Okay. So first of all, let me thank the organizers for giving me this opportunity to present my work in this colloquium. So today's topic of my lecture is quantum spatial aging algebra and its representations. So by representations, I mean irreducible representations or simple modules. They are equivalent. So this is a joint work with Shanu Bera. So let me first of all clarify what do I mean by quantum spatial aging algebra. Even Sanu gave a talk in the previous week where he discussed something called quantum affine space, quantum well algebra, and all this kind of stuff. So what are these quantum algebras? So these quantum algebras are broadly called quantum groups. So what are quantum groups? Now quantum groups are not groups at all. So they are algebra. Now the problem is that there is no axiomatic definitions of quantum groups available till date. Okay, so this is the biggest open problem that you can find in the area of quantum groups. Even there are no
it's a Hopf algebra.
Yeah, but that's a property. That's not a definition. So even there are no set of fixed properties are given to us that if an algebra satisfies this property, then you are going to say that algebra a quantum group. So there are some properties known, as Sad said, that it's a Hopf algebra, but mostly the quantum groups are nothing but deformations of our known rings, such as Sanu defined quantum plane. The definition was it was an algebra generated by two generators x and y satisfying the property xy is equal to qyx. So obviously this is the deformations of our known two polynomial ring with two variables. So in polynomial rings with two variables, the multiplication is defined by xy equal to yx. Here we are defining xy is equal to qyx. So roughly speaking, deformation of a ring means another ring where the addition remains the same, but the multiplication changes. Okay. So they are deformations of our known ring, such as he defined quantum well algebra. The definition of quantum well algebra was xy minus qyx equal to 1. Okay. And the definition
that vector space structure remains the same.
Yeah, the vector space structure remains the same, but the ring structure gets changed. I mean the multiplication. So even for quantum well algebra, the definition was xy minus qyx equal to 1. And the general well algebra of with two generators, it is defined by xy minus yx is equal to 1. So again, that's a deformation. The multiplication gets changed. And the adjective quantum, this refers to something called a solution of quantum Young-Baxter equation. So now these algebras that we are going to discuss, this algebra generally arises in quantum statistical mechanics. And in quantum statistical mechanics, people are interested into a solution of something called quantum Young-Baxter equation. So obviously you can find deformations of polynomial algebra with two variables. You can find a lot of deformations. Now, why we are going to say the definition xy is equal to qyx as the quantum version of the plane, that is quantum plane. There may be some other deformations. So why we are not saying those deformations as a quantum plane? Because one can prove that the definition xy is equal to qyx, the definition of quantum plane, that is the only algebra which satisfies the quantum Young-Baxter equation. So when generally a Hopf algebra satisfies a quantum Young-Baxter equation, it is called a quantum group. That much is known to us if we are talking about quantum groups. So I am saying all these things because this quantum spatial aging algebra, this is a deformation of one spatial aging algebra. That is easy to find. But the thing is that I haven't come up with any literature so far which basically discusses which quantum Young-Baxter equation this algebra is satisfying. You know, this algebra came into surface in 2016 and only 2 papers have been written on it. So maybe there is any paper, but maybe someone is working on it, but still I haven't found it. But still they are saying this is the quantum version of one specializing algebra. If you want to say it, then you need to make sure that it satisfies some quantum Young-Baxter equation. Okay, so this is the shortcoming of this talk. I don't know which quantum Young-Baxter equation it satisfies. But as I said, that there are some properties of quantum groups that are known to us. So one of the properties I said it's a Hopf algebra. So let us start from there. So Hopf algebra. A Hopf algebra is an algebra A together with k-linear maps. So whenever in this talk I am going to say an algebra A, it means an algebra over a field K. So there is an underlying vector space structure together with a ring structure on it. Now on an algebra we are defining three maps. One is called the delta map, which is called the co-multiplication, which is from A to A tensor A. This tensor product is over the field K. Then you have the co-unit map, which goes from A to K, and another map S, which is called the co-inverse or the antipode map, which is from A to A. So on an algebra structure, you have already got two structures. One is the multiplication, which goes from A tensor A to A, and another is the unit map, which goes from K to A. Now you are defining another three maps on them to get a Hopf algebra. So you can expect that these five structures, two on algebra and three here, they should satisfy some sort of compatibility relations. So I am not going there because these are pretty much lengthy calculations and lengthy relations that I have to write, but we don't need it. We just need the definition of an Hopf algebra. So that is what written here. So these maps must satisfy some properties, including that this epsilon becomes an algebra homomorphism, S is an anti-automorphism. All these properties that generally comes from those compatibility relation. Even this delta map and epsilon map, they itself satisfy some sort of relation, but we don't need to go there. If anyone is interested what kind of relation they satisfy, then they can consult a book written by Christian Cassel. The name of the book is Quantum Groups. It is published by American Mathematical Society. So the most useful Hopf algebra that we are going to use in this lecture is the first one, that is called the group algebra. So let G be a group, then the group algebra, we do know that it forms an algebra. So this becomes a Hopf algebra. So as soon as I am saying this is a Hopf algebra, you need to define the co-multiplication, the co-unit, as well as the co-inverse. So the co-multiplication is defined by LG is G tensor G, epsilon of G is 1, that is the co-unit, and the antipode or co-inverse is defined by SG is equal to G inverse. So this is a key example that will later allow us to generalize ideas from group actions to Hopf algebra actions. So we will discuss that later, that how Hopf algebra can generalize ideas of group action. Okay. So the second most important that we will meet is the universal enveloping algebra of a Lie algebra. So if you have a Lie algebra, then the universal enveloping algebra of that Lie algebra, that also becomes a Hopf algebra. So the co-multiplication is del of x is x tensor 1 plus 1 tensor x. Epsilon of x, the co-unit is 0, and the antipode map is minus of x. Okay. Next, we are going to define something called quantum SL2. So if you have an element q, this q is generally called the parameter in quantum groups. So we are taking a non-zero element and we are also saying this q is not going to be plus minus 1. Then given a simple Lie algebra G, we can define a quantum group UQG. Okay, so this UQG is nothing but the deformation of enveloping algebra over G. This also becomes a Hopf algebra. But the definition for general G, if you take a general Lie, a simple Lie algebra G, then the definition is quite complicated. So let us take a particular example. So we are taking SL2. So then UQSL2, it is basically generated by 4 generators, E, F, and K plus minus 1, together with these 3 relations. Okay. So the relations with K inverse can be found from the relation with K. So now this becomes an Hopf algebra. So if you say this is a Hopf algebra, then you need to define the co-multiplication, which is looking like this, and co-unit looks like this, and co-inverse looks like this. Okay. So this is the definition of quantum SL2. We'll need this. So this is nothing but the quantum version of universal enveloping algebra of SL2. So if you this is a deformation, and you can also prove that that this is the only deformation which satisfies the quantum Young-Baxter equation. So if anybody is interested into that proof that this is the only algebra which is going to satisfy quantum Young-Baxter equation, again they can look at Christian Castle's book. So now we are going to need some notation. This notation is called Swindler notation. So let A be an Hopf algebra, and you take a small a from capital A. Then this Dale map takes this A to A tensor A. So we are going to write this symbolically as A1 tensor A2. Mind that this sum should run from some I runs over 1 to n A I1 tensor A I2. We can write it as this, but that will increase the complexity. Because what will happen that the co-multiplication, as I said, they are going to satisfy some sort of compatibility relation. So one of the compatibility relation is that it becomes co-associative. So what is co-associative? Co-associative means this relation. Identity tensor delta, compose delta is going to be delta tensor identity compose delta. Okay. So this map, mind that this map on the left hand side as well as this map on the right hand side, this goes from A to A tensor A. So now if you want to write it, this notation, without this notation, in general how we write it, if you want to write it, that becomes pretty complex. So now with this notation, we can write this identity tensor delta over delta of A as simply A1 tensor A2 tensor A3. So these notations help us to write it pretty clearly. So we are not going to get into any sort of ambiguities. We can write it pretty clearly. So this Swindler notation will be useful later. So now we are going to this topic, generalization of group and Lie algebra actions. So when I defined the group algebra KG and proved that it became a Hopf algebra, so there I told you that somehow this Hopf algebra is going to generalize the actions of groups. So let's say if a group act on a ring by automorphism, then what is the definition? So the actions looks like this. So G is acting at automorphism. So on two elements R prime, G is going to act like this. G on R and G on R prime. And G is always going to take the identity element into identity element of R. Now, if a Lie algebra acts on rings by derivation, then for all x in G and R1 in the ring R, so x is acting as derivation, so it will act on R first, R1 remains same, and then R remains here, x acts on R1. And x acting on the unit identity element will be 0. So now, depending on these two, we are going to generalize this actions of groups and Lie algebras in terms of Hopf algebras. So we are going to define something called a module algebra. So let A be a Hopf algebra and R be a K algebra. And A module algebra structure on R is the data of an A module structure on R. So we are somehow trying to define a module structure on R, but now it's an Hopf algebra module structure. So how we are going to define for A in capital A and R1 in capital R? So the first definition is A is acting on R1 as the sum of A1 dot R and A2 dot R1. Mind that this A was in the Hopf algebra capital A, and this A has a Swindler notation, the notation that we used here. Sorry, here this Dale of A is A1 tensor A2. So if you take the co-multiplication on A, you will get this A1 and A2. So this A1 and A2 acts on R and R1. And similarly, how this A acts on the identity element, it acts as epsilon A of 1 of R. Mind that epsilon of A was in the ground field K. So now let us look at this thing. This module algebra structure somehow generalize the group actions. So if you do remember this group action G can be considered inside KG. Okay. So now G acting on R prime basically means that you need to look at what happens when Dale acts on G. So if you do remember, Dale acting on G was G tensor G. So this A1 was also G and this A2 was also G. So that's why you are getting G dot R times G dot R prime. And similarly, epsilon of G was 1 for every G. That's why G dot 1 of R gives you 1 of R. Same goes with the Lie algebra structure. If you do remember, del of x was x tensor 1 plus 1 tensor x. So when x acts on here, so x dot r, so you get the first thing, and the second thing is 1 dot r1. So that is only r1. And the second case, it's 1 dot r, and the second thing is x dot r1. And if you do remember, epsilon of x was 0 for the universal enveloping algebra. So there also you will get x dot 1 of r. So epsilon of x is 0. So on the right hand side, you are going to get 0. So this module algebra structure somehow generalize the group and Lie algebra actions on a ring. So as soon as you get this module algebra structure, out of this you can find a new algebra. Okay. So the new algebra is called the smash product ring. If you do remember, as soon as we defined the group actions, we could have find that fixed set of elements or fixed set of group elements in the group. So similarly here, you can also find some new rings. Basically, this becomes an hop algebra, by the way. So this smash product ring is denoted by R smash A. This is semi-direct product sign, but we will call it smash. So which is as a vector space is R tensor A. So as a vector space, it is the tensor product between R and A. But now I have to define the multiplication. So if you take two elements, R tensor A and R prime tensor A prime, so you could have multiplied it as R prime tensor A prime. But now we are going to use the co-multiplication structure on A. So del of A is some A1 tensor A2. So you can use this as R acting on A1 dot R prime tensor A2 dot A prime. So this multiplication is a bit twisted. You are going to use the co-multiplication structure on A. Okay. So that's how you can do this. So now there is an action of this UQSL2 that we defined on the quantum plane. So I was talking about quantum plane.
You have not defined what is A1 dot R prime.
Sorry?
You have not defined what is A1 dot R prime.
So A1 dot R prime is already defined here because you have already got the module structure, right? Module algebra structure. Because it's already a module structure. R has an A module structure. It will be called a module algebra if this two relation is satisfied. So this A1 acting on R prime is already defined because this has a module algebra structure. Okay. Is it fine?
Yeah.
Yeah. So now, as I said, there is an action of this UQSL2 that I defined. The quantum version of enveloping algebra of SL2 on the quantum plane. I was talking about that quantum plane. So the quantum plane is defined by this. This is a free algebra over x and y satisfying the relation xy is equal to qyx. So the explicit data is given by this. E acting on x as 0, f acting on x as y, k plus minus 1 acting on x as q plus minus
structure.
Huh?
This is you're defining a module structure.
Yes, I'm defining a module structure. So then you have to check that this module structure also satisfies the two relations of that module algebra. But that's easy to check. Even you have to check that E acting on xy minus qyx is basically 0. Okay, because this R also satisfies this relation xy is equal to qyx. But the explicit data looks like this. This defines an action of UQSL2 on KQXY. This defines an action of UQSL2 on KQXY. So now you have got this structure. So we can consider a sub-algebra of UQSL2 that I forgot to write. So we can consider a sub-algebra of UQSL2 and then structure remains the same because you already have a module structure of UQSL2 on R. So the sub-algebra will also have a module structure. So that's what I'm going to write here. So the quantum plane is a module algebra over the positive part, UQ greater or equals to 0 SL2 of the quantum enveloping algebra UQ SL2. So this UQ greater or equals to 0 SL2, it is known as the Borel subalgebra or the positive subalgebra of UQ SL2. So what happens that in UQ SL2 you have got 4 generators. So you can exclude this F. So the subalgebra generated by E and K plus minus 1, that is nothing but the subalgebra UQ greater or equals to 0 SL2. This is called the Borel subalgebra. So the structure remains there because KQXY became an UQSL2 module. So if you take a subalgebra that remains there, now you can define the smash product because it was going to be a module algebra. So this smash product is known as the quantum spatial aging algebra. So you already have a module structure, module algebra structure, so that from module algebra structure you can define the smash product. So as an abstract algebra, this quantum spatial aging algebra is a K algebra generated by the element E, K plus minus 1, X and Y subject to these defining relations. So there are 6 defining relations, EK is equal to Q to the power minus 2K and so on. So what is this E? This E is nothing but, please remember, as a vector space, this was nothing but KQXY tensor with UQ greater or equals to 0 SL2. So this E is nothing but one tensor E. K is nothing but one tensor K. X is nothing but X tensor 1. So we are denoting one tensor E as E, X tensor 1 as X, and then we can use the multiplication rule. The multiplication rule that was defined here. This multiplication rule. So if you do use this multiplication rule as an abstract algebra, you get this kind of relations. Okay. So now this is basically the deformation of one spatial aging algebra. Okay, that is an Lie algebra, that is a Lie algebra, but I haven't defined it here because I don't know why it is called the quantum version of the spatial aging algebra. As I said earlier, because I don't know whether it satisfies the quantum Young-Baxter equation or not. But still, this is a Hopf algebra. So you don't have to worry about whether this is a quantum group or not. This is a Hopf algebra, so we can study it. Okay. So generally, whenever you are studying this kind of algebra, which basically involves some sort of parameter, so this Q is called the parameter. So the study is generally divided into 2 parts. One part is where Q is a root of unity, which is called the non-generic case, and the other part is where Q is not a root of unity, which is called the generic case. So whenever you are going to study, you are going to study only one case, whether the non-generic case or the generic case. So what happens that if you are going to study the non-generic case, that means Q is a root of a unity, most of the time this kind of algebra, let's say this is a quantum group, let us just assume it right now. So if it is a quantum group, then if the parameters are somehow root of unity, it becomes a polynomial identity algebra. Okay, most of the time. So the polynomial identity algebra term was discussed by Sanu, and he discussed almost everything about it. So as soon as this becomes a polynomial identity algebra, you can study its polynomial identity degree. By the way, if you have a polynomial identity algebra, then finding its PI degree or polynomial identity degree is not a trivial problem. Sometimes you will not be able to find it. Okay, so all the time you will not get success, but still you can look at it. And this algebra was basically introduced by Vladimir Babula and T. Lu in 2016. And they have written 2 papers on it. Mostly they have studied the generic case, that is where Q is not a root of unity. They have studied the primitive ideals, prime ideals, torsion modules, weight modules, etc. In our lecture, we are going to assume that this Q is a root of unity, and further we are going to study. So from here on, whatever results I am going to discuss, this has been done by us, that is me and Shan. And Dr. Gupta hasn't checked it yet, so it may happen he can find out some sort of error and this talk may have a premature ending. So I don't know what will happen or not, but both me and Sanu have checked these results quite a few times, so I don't think there will be any kind of mistake. So the first result is that k to the power L, e to the power m, x to the power n, y to the power p, where L is an element from integer z and m and p are non-negative integer. So this becomes a basis of this quantum spatial aging algebra. So it's pretty important to find whether this kind of basis do exist in the quantum groups or not. This kind of basis is called the PBW basis or Poincare-Birkhoff-Witt basis. So you can use Diamond lemma to find this basis. I think Diamond lemma is known to everyone. The calculations are not tough, but it's lengthy. there will be no inclusion ambiguities, but I think there will be 4 overlap ambiguities, and you have to calculate a lot to find this basis. So what is the facility of getting this basis? I mean, what is the advantage of finding such a basis? There is no guarantee that every quantum group is going to have a basis like this. I mean, a PBW basis like this. The facility, I mean, the advantage of getting this kind of basis is that as soon as you get this as a basis of a quantum specializing algebra or any quantum group, you can write that algebra as an iterated skew polynomial ring. So the term iterated skew polynomial ring was also defined by Sanu, so I am not going to get into that. So you can write this quantum specializing algebra as an iterated skew polynomial ring like this, where this tau 1, tau 2 and tau 3 are automorphism. Mind that tau 1 is an automorphism of k plus minus 1, tau 2 is an automorphism of this thing, tau 3 is an automorphism of these 3 terms, okay, and del 3 is a derivation of these 3. So these are defined by something like this, okay. So this calculation is pretty easy. The theorem, the second theorem that has been stated here, once you somehow find the basis, then it's pretty easy to define the algebra as an iterated skew polynomial ring. So now, what is the advantage of writing the algebra as an iterated skew polynomial ring? As I said, when this parameter q becomes a root of unity, most of the time the quantum group will become a polynomial identity algebra. But as I said, to find the pi degree of an pi algebra is not easy. So there are no perfect algorithm that we can find. But as soon as we write the quantum group as a skew polynomial ring, you can use something called derivation deletion. So what is derivation deletion? You can delete this derivation. Okay, there is only one derivation. Even if there is finitely many derivation, you can delete every derivation. Okay, so that is the thing that has been proved in the theory of polynomial identity rings. So if you have a iterated skew polynomial ring, then its pi degree is going to be same to another iterated skew polynomial ring where you just delete the derivations. Okay, now as soon as you delete this derivation, what happens is that the new iterated skew polynomial ring becomes a quantum affine space. Okay, the term quantum affine space is also discussed by Sanu in the previous lecture. And as soon as you arrive in quantum affine space, there is a perfect algorithm to find out the polynomial identity degree of an quantum affine space. Sanu also discussed that theory is generally proved by Processi and De Conchini. So what happens that as soon as you write this quantum spatial aging algebra as a iterated skew polynomial ring, you can now use this derivation deletion thing and find out its pi degree. So now we are going to assume something. We are going to assume that the ground field is an algebraically closed field of characteristic 0. This basically helps to delete the derivation. Okay, if you don't assume characteristic 0, then you need some extra condition on the derivation. I think you need the derivation has to be nilpotent. Okay, so we are not going into that. We are just assuming the field is of characteristic 0, and this algebraically closed thing will be needed later. So we are just going to assume K is an algebraically closed field of characteristic 0, and now we will prove this theorem. I mean, it's pretty easy once you write it as a iterated skew polynomial ring. So if this parameter q becomes an lth root of unity, that is q to the power l is equal to 1, then the quantum spatial aging algebra becomes a pi algebra, and its pi degree is L square if L is odd and L square by 2 if L is even. Okay, now as soon as you get this pi degree, what happens that you can somehow relate the representations or irreducible representations with this pi degree. So the first thing is that if q is a root of unity, since this quantum group becomes a pi algebra, so all its irreducible representations or its simple modules, from now on I am going to say simple modules, so all its simple modules are going to be finite dimensional. So you are not going to get any infinite dimensional simple module, and the dimension of the simple modules will be bounded above by the pi degree. So that's the result, it's there. So now you can say that all the simple modules of this quantum spatial aging algebra is bounded above by either L square or L square by 2, provided L is even, odd or even, respectively. Okay. So as I said, the to find the pi degree, it's kind of pretty difficult. Now, what happens if you can't write the quantum group as an iterated skew polynomial ring? Then you don't have any algorithm. So then you can take the toughest route. The toughest route is to somehow classify all its simple modules. Okay, you do know it's a pi ring, so its simple modules are going to be finite dimensional. So you can classify all its all its simple modules, and the maximal possible dimension of the simple modules is going to be your pi degree. But classifying simple modules over a non-commutative algebra is a highly non-trivial problem. I mean, there is no fixed algorithm how to classify the simple modules. You can just use the trial and error methods and you can get lucky. Sometimes you can't. Such as Sanu described something called quantum well algebra. This quantum groups was introduced in 1980s. So it has been 41 years. Nobody has been able to find the simple modules or classify simple modules over quantum well algebras. Okay. I mean, let alone the general n, the only result that has been found till date is for n is equal to 1. So that's an algebra with 2 generators, only 2 generators, the easiest possible case. Even for n is equal to 2, nobody has found it. So we tried it a bit, but we also couldn't find that. So if you want to find the pi degree of a quantum well algebra via the toughest route, that means finding all simple modules and somehow get the maximal dimension, then it's quite impossible. Okay, so Sanu did it. I think Sanu also told you the result because he was running out of time, so he couldn't focus on that, but he told you the result, what is going to be the pi degree of a quantum well algebra. Okay, and that was computed by this method, not by classifying all simple modules. But here we are going to classify all the simple modules of this quantum spatial aging algebra. Okay, so before that we are going to assume something. So first of all, we are going to assume Q is an odd Lth root of unity. So L is odd. And the second thing, that all modules are right modules. So now there are few observations. First of all, e to the power L and k to the power L become central elements of this quantum spatial aging algebra. It's pretty easy. If you do look at the definition, these are the definition. Now Q becomes an Lth root of unity. So as soon as you put e to the power L here, you will get q to the power minus 2L here. And since L is odd, so q to the power q square is also an Lth root of unity. So you are going to get 1 instead of any parameter. So similarly, if you use k to the power L, you will get the same result. It is because q is an odd Lth root of unity. So these are central elements. And if you find any central elements on a simple module, they are going to act as constants or scalars on the simple module. I mean, you already have assumed that K is an algebraically closed field, so you are going to get an eigenvector, and that eigenspace of the central element that will become a submodule of the simple module n. And since you are talking about submodule of a simple module, non-zero submodule, because eigenspace are non-zero, so that submodule is going to be whole of n. So from there you can prove it. It's pretty easy. Okay, so central elements are always constant on a simple module. Now note that on the algebra, K inverse also existed. So K becomes an invertible operator on the simple module. So this alpha 2, K to the power L is alpha 2 on the simple module n. So this alpha 2 has to be non-zero. We can't comment anything about alpha 1. We don't know how alpha 1 is going to behave. It can be 0, it can be non-zero. But for sure, alpha 2 is going to be non-zero. Now, this phi is defined by x plus 1 minus q square q inverse y. Okay, now you may think out of blue where this phi came up. So this came up due to a back calculation. I will let you know how we got this phi, but just assume that this is phi and this x, they are all normal element in the quantum spatial aging algebra. And even normal element on a simple module acts either 0 or invertible. Okay, it's pretty easy. So if you take a kernel take the kernel of a normal element that again becomes a submodule of the module. Okay, since it's normal means it quasi-commutes with every generator. Okay, so you can use that quasi-commutation relation and can prove that kernel is going to be a submodule. So kernel is going to be a submodule, that means kernel is either 0 or kernel is whole of n. If kernel is whole of n, then it's basically 0 on the simple model. And if kernel is 0, mind that as soon as you assume that Q is a root of unity, this became a polynomial identity ring. So this simple module became finite dimensional. So on a finite dimensional module, on a finite dimensional vector space, X is an operator and phi is an operator. So if you get injectivity, that will imply surjectivity. So from there you can prove that it is an invertible operator. So we are going to assume that phi and x are all invertible. So what happens if phi and x are 0? So if both phi and x are 0, then n becomes a simple module over quantum affine space. And the simple modules over quantum affine space has already been classified by us. That was the result that Sanu presented in the previous week. So we are going to assume that both this phi and x, they are invertible on the simple module. Now x and ye, they are commuting operator, and on a finite dimensional space, if you have commuting operator, they are going to have some common eigenvector. So x and ye have common eigenvector. Say that eigenvector be v. So v of x,
suppose that phi, you said that x-axis 0, then that is fine. You can get you will reduce to quantum affine space.
yes.
But what happens if phi x is 0?
Yeah, so that phi relation, it doesn't clear from here, but the phi relation you can reduce it to ey minus q to the power minus 2 ye. Okay, so this phi has another notation. You can write is as ey minus q to the power minus 2 ye. Okay, so if phi is 0, mind that, look at the definition, the only problem, the only derivation that was arising because of this, look, ey is x plus q inverse y. Okay, so as soon as phi becomes 0, then e and y also start quasi-commuting. So as soon as they start quasi-commuting, look, the other generators are quasi-commuting. So you are going to get into a quantum affine space.
Yeah,
okay,
but I'm asking about phi.
Why?
Suppose phi is acting as 0. Phi,
Yeah.
phi,
Yeah.
normal element.
Yeah.
Right. So suppose that is acting as 0. Right. Then what is what will happen? Yeah,
so that basically means that e and y starts quasi-commuting. So we can say that n becomes a simple module over the quantum spatial aging algebra mod phi.
if you go to the IC, so because x will be some scalar multiple of y, that is why.
Yeah.
Okay, fine. That's fine. Okay.
Okay, so now Vx is lambda 1v and V of y is lambda 2v. Now we have already assumed that x is invertible. So this lambda 1 cannot be 0. Okay, we are not commenting anything about lambda 2 because we will not need it. But this lambda 1 is non-zero, that we are going to use later. So now mind that this e to the power l, which was acting as alpha 1 on the simple module, I said that we don't know whether this alpha 1 is 0 or non-zero. So the first case, we are assuming that alpha 1 is non-zero. That means the action of e to the power l on the simple module is non-zero. So now we are going to consider the subspace n1 of n. N was the simple module over quantum spatial aging algebra. We are considering a subspace n1 which is generated by the vectors e(a1), a2. So what is this e(a1), a2? This is nothing but v e to the power a1, a to the power a2. This basically means that e to the power a1 is acting on v, and after that a to the power a2 is acting on this whole thing. Okay, because it's a module, so the generators e and k is going to act on this v. And mind that the range of a1 and a2 is from 0 to l minus 1. Okay, so you have l square many elements and you are generating a subspace n. Then and mind that all these elements are non-zero elements. as soon as you assume that alpha 1 is non-zero, that is e to the power L is non-zero on the simple module, E becomes injective. Okay, and K was invertible because K inverse existed in the original algebra. So all this element E, A1, A2, they are non-zero. It's pretty important to get non-zero elements. Okay, so all these L square elements are going to be non-zero. Then I am saying this N1 has a submodule structure. Okay, so N was the module we defined a subspace N1, and I am saying now this N1 becomes a submodule. So how? So now we have to somehow define the actions of the generators on this subspace N1. So now the first generator is E. So how E A1 A2 is acting on E? So instead of E A1 A2, you can write V E A1 K A2 E. Now this K and E, they can quasi-commute among themselves, and that will give rise to the scalar Q to the power 2A2. Now E comes here, so you can add E here, so you get E to the power A1 plus 1. So you get into E A1 plus 1 comma A2. Sorry, I have made a mistake. This scalar should be here. It should be Q to the power 2A2 times E A1 plus 1 comma A2. Okay. Now this is pretty interesting. Note that if you start from 0, you act E, let's say A1 to be 0, and you act E, so you are going to get 1. So that's how you can keep increasing. But what happens if A1 becomes L minus 1? So now if A1 becomes L minus 1 and you act E, you are going to get L here. But note that the range of A1 is between 0 to L minus 1. So what happens there? So as soon as you have L minus 1 instead of A and you are acting E, you are getting E to the power L here. This A1 plus 1 becomes L. And note that E to the power L acts as a scalar on the whole of the simple model. So on V, it's going to act as alpha 1. So this A1 plus 1 basically reduces to 0 because there will be no E there. Okay. So if A1 becomes L minus 1 and you act E on it, you are going to get back to A1 is equal to 0 with some scalar in it. So this is a kind of cyclic process. You start from 0, you keep increasing it up to L minus 1. Then again, if you start to increase it, you go back to 0. Okay. So now what is E A1 A2 acting, X acting on E A1 A2? So now again you write the definition of E A1 A2. This X is going to quasi-commute with both K and E. Okay. And note that we have already defined V of X is lambda 1 of V. So this X comes here quasi-commuting. So you are going to get this scalar Q A1 plus A2 and you are going to get Vx. Now V of X is lambda 1 of V. So you can replace V of X by lambda 1 V. So what you got? You got Q A1 plus A2 lambda 1 times E A1. Okay. So again, so it basically look that this E A1 A2 becomes an eigenvector of the operator X corresponding to the eigenvalue Q to the power A1 plus A2 lambda 1. Why I am saying this is an eigenvector? Note that to tell this is an eigenvector, I need to make sure this is a non-zero element for every A1 A2. That's why it is defined like this. That's why I was saying that all these E A1 A2, this L square many elements that I have chosen from N, they are all non-zero. Okay. Now, what about K? So it's pretty easy. If you act K, this K gets added with K to the power A2. So you get.
So how do you know that all the E A1 A2 they are non-zero?
Yeah, because E to the power L is non-zero now. You have assumed alpha 1 is non-zero. So let's say if you find some V of E is basically 0, that will basically means V to the power L is also 0. Is it fine?
Yes. No, it is not fine because you have V e to the A1 K to the A2. Okay, and K is an invertible element, right?
Yes. Yes.
So in the spatial algebra, quantum spatial algebra, I mean, without giving the presentation as an iterated skew polynomial ring, in the spatial algebra case, an invertible element is a unit.
Yes, yes, K inverse exists there.
Achha, achha. So
just look at the definition again if you have any problem. Yeah, so look, these elements are generated by E, K inverse. Okay.
I see. Very good. Okay. Then you come back to the definition. Okay, and so times A. Okay. Yeah. So fine. Okay, now I'm happy that EA1, A2 will always be non-zero.
Yes. Okay. So now what is the action of y? That is only left, because you don't have to define the action of K inverse. The action of K inverse can be obtained from this action of K. So now if you want to define the action of y, so note that this y quasi-commutes with K and you get a scalar q to the power minus A2. Now you can use the commutation relation between E and y. So what is that? So if you use the commutation relation between e to the power A1y, you get something like this, the thing that is in the first bracket. Okay. So now you can take e to the power A1 minus 1 outside. So here ye remains and here x remains. And note that we started with v of ye is lambda 2v and v of x was lambda 1v, because ye and x are commuting operators. So they had that same common eigenvector v and we started with that v. Okay. So look, you got this. You got this big scalar coming in front, and now you got this a1 minus 1 comma a2. But now there is again a catch. So what happens if a1 becomes 0? Then again it becomes minus 1, a1 minus 1, but there is no minus 1 in the range of a1. a1 is from 0 to l minus 1. So that's why I have written an a1 greater than equals to 0 here. So I need to discuss what happens if a1 becomes 0, how y acts on them. So now if a1 becomes 0, so you have e0 comma a2 acting on y. So what is e0 comma a2? It is only v a a2y. Now I am going to use that this alpha 1 is non-zero. So alpha 1 is a scalar, it's a non-zero scalar, so its inverse exists in the field. So you can use alpha 1 inverse. Okay, I have done one step jump here. So alpha 1 inverse alpha 1 v. That's what I am going to write. And instead of alpha 1 v, you can write v e to the power l. Okay. So I am going to use, I just use that alpha 1 is non-zero. Okay. So I used alpha 1 inverse alpha 1 v, and instead of alpha 1 v, I wrote v e to the power l, because the action of e to the power l on the whole.
Just go back to the previous slide. Okay.
Yeah.
Just go back to the previous. Just go back to the yes. Yes. So why do you want that these a1 a2 they should be non-zero?
A1 A2, because I am going to use it later that they are all eigenvectors corresponding to some operators. So that's why I am saying they are all non-zero.
They are eigenvectors corresponding to some operators.
One operator is already given. Look, this they are eigenvectors corresponding to x.
Yeah, they are eigenvectors corresponding to x. Yes.
Yes. So I'm going to use this again later. In the later part of my talk, I'm going to use them. That's why I'm saying they are all non-zero.
Yes.
Okay. Yeah. So that's why I use that alpha 1 is non-zero. So you can introduce that alpha 1 inverse. And now you can use the same relations again. The same thing that I did here. Okay. In case of y. So you get this thing. So when you have a1 is equal to 0 and you apply y on it, you go back to l minus 1. Okay. So you don't get minus 1, you go back to l minus 1. So basically this a1 and a2, the thing that I defined here, this a1 and a2, they are basically acting in between z of l, z mod l. Okay. So from 0 to l minus 1, look, the action is somehow defined like that. Their range is 0 to l minus 1, but as soon as you arrive l minus 1 and you try to increase it, you go back to 0. If you arrive at 0, you try to decrease it, you go back to l minus 1. Okay, so they are all varying in between z mod l. So now we have defined all the action of the generators on my subspace n1. So let us go back again. The n1 subspace was generated by all these elements e, a1, a2, and I have defined the actions of every generator e, x, a, and y. So this n1 becomes a submodule. And mind that all this submodule contains elements which are all non-zero. So this is a non-zero submodule. So it has to be equal with the whole simple module. So the problem of classifying simple modules is done here. Okay. So classifying simple modules means that you have to somehow define the action of the generators on the simple module. And now we have defined the action of the generators on this simple module. So this N1 is nothing but N. Okay. So now
simple modules not just means that, I mean, because your parameter, you have some parameters like alpha 1, etc., alpha 1, alpha 2. So classification also means, I mean, describing when they are isomorphic, two modules that you are defining.
My simple module doesn't depend on the parameter alpha 1. I mean, alpha 1 is just e to the power n, but it's not a counter.
No, you are assuming that some power of this generator, this is acting as the scalar matrix, right?
Yeah.
Alpha 1 times I.
Yeah.
So, I mean, that alpha 1 is a kind of parameter for this simple module that you are, because you see that if there are two, it can happen that there are two different simple modules, and these, I mean, the scalar that you obtain, they are different. Okay, so if the scalars are different, then they cannot. Then can they be isomorphic?
Yeah, that I think I have to check, but I don't think that. I mean, why we should get two different scalars? Because I am starting with a simple module. As soon as I start with I am not constructing simple module. I am basically classifying the simple module, how the action will be. So the simple module is already given to me. The simple module is n, and now I have to tell how the generators is acting on that simple module.
Yes, you have defined, but when you are defining the action of the generators, right?
Yes.
Then the scalar pops out, right? Which is this, this alpha 1 and also alpha 2, and so this and these lambda 1 and lambda 2. So these scalars pop out, right? The scalars pop. So now, I mean, the point is that if you take different simple modules, then these scalars may be different.
Okay. Now I get it. Yeah, that's true.
So classification does not just mean describing how the generators act, right? So you are describing the. This is a first step in the classification. This is a significant step. But to complete the classification, you should also describe that these parameters that are coming into the picture. How do the simple modules, and these parameters, they determine whether, what are the you have to describe that
so given two different parameters, isomorphic. I mean, the isomorphic class.
Yes, different sets of parameters that you are getting can give the same isomorphic. They can give you isomorphic modules or not. Okay, that is the question.
Yeah. So okay, that's fine. I will do that later. So now the thing that is still remain to do, because we want to somehow relate this with the dimension. We want to somehow relate it with the pi degree. So to relate it with the pi degree, we need to find the dimension. So I am saying that n has dimension L square. Mind that n was generated by L square many elements. Okay, basically we started with n1. N was generated by L square many elements, but later we showed that n1 is equal to n. So now I have to show that n has dimension L square. So now if you take two different generators, E A1 A2 is not equals to E B1 B2. then two following cases can arise. The first case is that q to the power a1 plus a2 is not equals to q to the power b1 plus b2. Okay. Then this e a1 a2 and e b1 b2 are both eigenvectors of the operator x corresponding to distinct eigenvalues. Okay. So let us go back to the action of x on e a1 a2. So as I said, that look, the action of x on e1 a2 gives you an eigenvector q to the power a1 plus a2 times lambda 1. Okay. Now lambda 1 is non-zero. So if q to the power a1 plus a2 is not equals to q to the power b1 plus b2, which we assumed, then obviously you are going to get eigenvectors corresponding to different eigenvalues, and that will basically means that they are linearly independent. Okay. So this means that e a1 a2 and e b1 b2 are linearly independent. Now what happens if they are equal? I mean q to the power a1 plus a2 is equal to q to the power b1 plus. So that basically means that a1 plus a2 is congruent b1 plus b2 mod l, because q was an lth root of unity. Okay. So now I am saying that e a1 a2 and e b1 b2 are both eigenvectors of the operator ye. So the action of y on e a1 a2 was defined, the action of e was defined, so I can define that, I can get the action of ye. So look, the action of ye is something like this. Okay, so if you go back just one thing, look, e increases a1 by 1 and then y decreases it by 1. So if you apply y first, you get a1 minus 1, and then if you apply e, you get a1 back. Okay, so this is the scalar that we are going to get. Now I am going to say that they are the scalars if e a1 a2 is not equals to e b1 b2, so we are going to get two different eigenvalues. So I am going to say that okay, the eigenvalues are distinct. So if they are not distinct, if we assume this is the eigenvalue of e a1 a2, this is the eigenvalue of e b1 b2. So if they are equal, you are going to get this kind of relation. Okay. Now,
yeah, but what happens if a2 is equal to 0?
If a2 is equal to 0, so yeah.
Because you have a different rule for, I mean, dealing with that.
We don't need a2 is equal to 0. I think we don't need a2 is equal to 0, because if a2 is equal to 0, then just look at this thing. Here you don't get any a2, so you are only going to get a1. Okay, so you can carry on like this.
See, if I'm saying a1 is equal to 0.
Yeah. A1 is equal to 0.
See, what you are, the action of y that you are defining,
yeah,
on e a1 a2 and also e b1 b2 is assuming that a1 and b1 are both non-zero.
Yes, yes.
Okay.
Yeah.
But suppose that either one of them or both are non-zero, then the equation changes. If you look at the top line of your slide, this is how the action is defined. There's something different to the other cases.
Yes.
Where
so, no, the same thing happens. If a1 is equal to 0, so what you are going to get? You are going to get q to the power minus a2 lambda 2 as scalar here. And now if you act e on it, just let me go there. So if you act e on it, you get q to the power 2a2. So together here q to the power 2a2 and here q to the power minus a2. So together you get q to the power a2. Now in this relation, in the last relation, put a1 is equal to 0. So again you get q to the power a2. As soon as you put a1 is equal to 0, this thing vanishes. The thing with lambda 1.
But see, if you go back to the previous slide, right? If you look, yeah, previous slide, and you are defining the action of y.
Yeah.
So the action of y is, I mean, the action of y is entailing this, I mean, this complicated kind of expression lambda 2 plus q times 1 minus q to the 2a1 by 1 minus q square, okay?
Yeah.
Times lambda 1.
Yeah.
So this term will not arise if a1 is equal to 0. That is what I'm saying.
No. That will arise. Just look at that. That was I was saying. If you put a1 is equal to 0 here, what will you get? you will get lambda 2 times q to the power a2, right? In the last relation, that's what I am saying. If you put a1 is equal to 0, so here you get 1 minus 1. So this thing vanishes.
Yeah.
So you get only lambda 2 times qa2.
Yes.
So here you are also getting lambda 2 times qa2, the action of ye. So look here, you are getting q to the power minus a2, lambda 2, and the action of e will give you q to the power 2a2.
Okay,
So
okay, so you can continue. I think
same thing happens. So now this thing, just focus on this thing, lambda 2 plus q by 1 minus q square lambda 1. So in the previous slides, I defined something called phi, and I said out of the blue that kind of complicated relation came. So what we notice that this thing, this lambda 2 plus q by 1 minus q square lambda 1 is nothing but the eigenvector of this phi. Okay. So we got that phi, that complicated relation from here, because we were somehow trying to prove that the first term in the third bracket is 0. So now phi was invertible, so this thing cannot be 0. Okay. So you get q to the power a2 minus a1 is equal to q to the power b2 minus b1. So basically you get a2 minus a1 congruent b2 minus b1 mod L. You already started with a2 plus a1 congruent b2 plus b1 mod L. That was our assumption while starting the case 2. So you will get a1 congruent b1 model and a2 congruent b2 model. Here we are using that.
What I was trying to point out was that this expression that you're getting lambda 2 plus q by 1 minus q square lambda 1,
Yes.
will this also arise if the a1 is 0?
No.
That will not arise.
You will only get lambda 2. Okay.
Yes. Then how will you argue in this case?
Yes. So then obviously lambda. So you get q to the power a2 lambda 2 only. Okay.
Yeah.
So there obviously then so it can also be proved, but you have to do another 1 or 2 cases more, because then
you have to check all the 4 possibilities. Okay.
No, that's fine. It's not that difficult. I mean, what are you going to get? So I am saying that a1 is 0. So just keep going with that, because in here if you put a1 is equal to 0, you get the same relation. So you are going to get q a2 minus q b2 is equal to 0. Okay. Right?
Okay.
So now how q a2 minus q b2 can be 0? Because a2 and b2 are basically in between the range 0 to l minus 1, and q is an lth root of unity, right? Because you are going to get a2 congruent b2 model.
Yeah. You will get a2 is congruent to b2 model.
Yeah. So that basically again create a contradiction.
That will create a
contradiction. That's what we want. We want a contradiction. Okay, so we want a contradiction because we just assume that they are going to be eigenvectors corresponding to distinct eigenvalues. So
you check all the 4. You should check all the 4 possibilities, right?
Yeah, I mean,
this is only one possibility.
Okay. I'll do that later. But from here, I think it can be deduced. Okay. So that basically means that if you get a1 congruent b1 model and a2 congruent b2 model, this basically implies that you are getting e a1 e2 is equal to e b1 b2, because as I said that this a1 and a2 they are from z mod l. So this is a contradiction because we started with 2 different generators. So now you can use induction to prove that this L square many vectors are linearly independent. We proved for n is equal to 2, because even we don't need to prove for n is equal to 2, for n is equal to 1 and then for the general case, but to prove the general case we need this, that given 2 distinct vectors they are going to be linearly independent. So that was our goal. We wanted to classify the same.
I am not fully sure that how you will be proving this L square independent vectors using induction.
Yeah, I mean, so if you take any combination, okay, so you take any combination and prove it to be to take the linear combination and let it be equal to theta. Okay. So since you have these properties that they are distinct eigenvectors corresponding to distinct eigenvalues, you can use that property and somehow reduce the length. Okay. So if you have L many vectors, linear combination of L many vectors equal to 0, you can use the property they are going to be eigenvectors corresponding to distinct eigenvalues, and somehow use it and reduce it to a linear combination of L minus 1 many eigenvectors. Sorry, L minus 1 many vectors. And then you can use induction, because for L minus 1 the result is true, and from there you can proceed. I mean, all the properties
Which operator you are acting upon to get the eigenvalues?
Yes.
Which operator you are using?
So either you are going to use X or you are going to use Y, depending on how they are going to behave.
Yes, but I think that it is better that you write down the details of all these.
Yeah, I mean, yeah, it is in the paper, but I thought, I mean, it's quite clear here, so I didn't mention everything. It will get a bit complicated if I write everything. But yeah, it can be done. I mean, we have done it in the previous cases. If you do remember, when we discussed quantum Well algebra, we did the same thing. Okay.
No, but you said at the beginning of the talk that I would be expected to check that your,
yeah, that's
correct. I cannot be 100% unless I know what is the, proof for, showing the case of n vectors are independent. Okay.
Yeah, but yeah, I will let you know. I mean, all the detailed calculation I will send you to them. Okay.
But
so just I think my time is running out, and I just need to do one thing. What happens if alpha 1 becomes 0? So I'm just going to tell you the construction, because mind that when alpha 1 was not equals to 0, our construction was dependent on this stuff, this n1, okay, generated by all these vectors v, e, a1, k. But if alpha 1 becomes 0, you can't do that. So the thing that we are going to do is something different. So we are assuming R to be the minimum index such that v e to the power r is non-zero. Okay. Now r is the minimum index. That means v e to the power r plus 1 is 0. V e to the power r plus 2 is 0. So I don't have any clear idea what is r, but I am saying r varies between 0 to L minus 1. Because v e to the power L is obviously 0, because we have assumed alpha 1 to be 0. So I am defining v1 as v e to the power r. And now I am saying let k be the minimum index such that v1, y to the power k acting on v1 is 0. Okay, so
okay, now the time is nearly up.
Okay.
So perhaps these further details we can discuss with me, right?
Yeah.
But we can finish the talk more or less, I think. Okay, if you want.
Okay, I mean, I just wanted to say this thing. So if you assume this k to be minimum such that v1 y to the power k is 0, so our claim is k cannot be less than L. So if you assume k is less than L, you will get a contradiction. Okay. So now you can use this as your E1, E1, A2. Okay, which is v1 y to the power a1 and k to the power a2, where a1 and a2 varies between 0 to L minus 1. And if you take this subspace, you are going to get the same result. The same actions, same as dimension as L square. So what is basically proved that all the simple modules over quantum spatial aging algebra are maximal dimension simple modules. They are going to be L square. Okay. And just one thing that I wanted to tell right now. So what happens if Q is an even root of unity? That problem is still left open, because I think there are some sort of problems there. And what about the whole smash product? KQXY smash product with UQSL2. We only took the positive part of UQSL2. So this was again introduced by V. Vabula and T. Lu. And here they didn't mention it to be any quantum group. They didn't name it. They just name it as the smash product of this. And this smash product is basically generated by 6 generators together with 10 relations. So things get pretty complicated here. So again, classification of simple modules, this is also open. Even this is a PI ring, but I don't know whether any PBW basis exists. So you don't know whether you can write it as an iterated skew polynomial ring. So everything related to this is open. Okay, so people can really look at it. So thank you. That's all for today.
Yeah, thank you very much for an impressive research talk. So are there questions from the audience?
Okay, I have a few questions.
Yes, please.
So, yes, Snehashis, can you go back to the last slide?
Yeah.
So you said if Q is not an even root of unity, so this means that what you have done is for an odd root of unity.
Yes, yes.
So where are you using the, I mean, where have you used the fact that L is odd?
Here, here. Just note that you got A2 minus A1 congruent B2 minus B1, and you already got A2 plus A1 congruent B2 plus B1. So from here, what you get? You get 2A1 congruent 2B1 model. Now, if L is odd, then you can cancel out that 2 and get A1 congruent B1 model.
Okay, excellent. Okay. So, I mean, you need to check still. I'm a little worried about what happens when A1 or B1 is 0, right? So all those cases you need to check. Okay, so this is, I mean, this remains intact even in those cases you need to check. And okay, so, and you also made a statement that, I mean, all the simple modules have dimension L square.
Yes.
Okay, so the point is that you are assuming here that some, for example, you're assuming that X is acting as, X is acting, you're assuming,
as an invertible operator.
But what happens if it does not act like that? It means that
so if X, then X becomes 0 on the simple model. So that basically reduces to the question of a quantum spatial, quantum affine space. Simple models of a quantum affine space.
Yes.
Yeah. So, so you don't want to go there. You just want to study the simple models of a quantum spatial aging.
Yes, but you know, this is also a valid case of the quantum. I mean, quantum spatial algebra, can it not act as in a case, you can have a case of this simple module where X is acting as 0. That is also a simple module over the spatial algebra, right? We cannot say it's not a module over the spatial algebra.
Yeah.
So, like it happens for the quantum affine space, that some of the generators start acting as 0. So then you get, I mean, smaller dimensional modules.
Yeah, that's true. Yeah.
You cannot assert that every simple module will be L square, right?
Oh, I mean, my sense was something like that, because when you start considering quantum spatial aging algebra, the simple modules are all maximal dimension. But that's true. Even if X is equal to X acts as 0, I do believe the dimension will be either L or L square. It cannot be 1 or something other than that.
So that, I mean, you need to modify that claim accordingly.
Yeah. So I think I should be careful about making that statement that all simple modules are maximal dimension modules.
Yes, yes. Yeah. And other thing is that, I mean, how you said that. How did you get the normal element? I'm just curious to know.
Yeah. So that normal element came from here. So we got stuck at this thing, this Q A2 minus A1 minus Q B2 minus B1's product with this equal to 0. And we wanted only this thing to be 0, the first term in the third bracket. So we are just investigating where this lambda 2 plus this thing came up. So we later find out that this thing is nothing but the eigenvalue corresponding to the operator phi. So from there we constructed that phi, and then we checked that it became a normal element. So we can assume that phi is invertible and carry on the calculation.
Okay, and do you have any idea about the center of this quantum spatial algebra? I mean, because you said E to the L and K to the L, they are central elements.
Yes, they are central, but yeah, I haven't calculated it explicitly what is going to be the center.
But at least are you able to show that this algebra is finitely generated as a module over its center?
Yes, you can take the nth power of any generator. I mean, you take the nth power of those 4 generators, and you will get the result, right? So it becomes a finite model. You don't need to exactly find the center. You can take central elements and generate the algebra.
So you mean to say that all the 4 powers of these generators,
Yes.
they will, I mean, they will.
That will be a central subalgebra. That will be a central subalgebra, and we just only need that, right? Finite dimensional module over a central subalgebra.
Finitely generated module over a central.
Finitely generated module over a central subalgebra.
Yes, but at the same time, you need to show that it's finitely generated, and for that, if you have calculated this basis, right?
Yes.
I mean, then that will serve the purpose. I think that will.
Yes. That's why calculating the basis, PPW basis, is pretty important for this quantum specializing algebra.
Yes, but so I will suggest that you also show that this is a PI algebra, also using this alternative approach that this is finitely generated as a module over a central algebra.
Yeah.
Right?
Okay. Yeah.
Okay, then thank you. So one comment that if all this is correct, then I think that this is something I mean publishable. Okay. Okay. All this is correct. And of course, you can improve upon along the lines we have discussed. Okay, thank you.
Okay, thank you. Thank you very much. Are there any other further comments or questions from the audience?
Hello.
Yeah,
Yes.
please.
Hello, Snehashis, I am Dwepan.
Yeah.
And so I have a question. I don't know these things, but I just want to ask that. So we have something relation and you want to classify. So what I want to mean that you are defining some actions, right?
Yes.
So my thing is that I mean when we ask any questions about classification, you need to show that whatever be the action may be, these are the only case. But you are defining some particular actions. And what if we define some other actions, there will be some in other different things will come up. I mean.
Yeah. That is what Assessor was telling me. To find out the isomorphism classes of the simple model.
Yeah.
That's a legitimate question, I guess. I mean, I just didn't get attention to it, but yeah, that's a good question. I mean, we need to find that also.
Okay. Thank you. Okay.
Yeah, thank you. Further comments or questions? Okay. Yeah, if not, then let's thank the speaker again for an impressive research talk. And probably some nice paper is coming out of that. Yeah, then next talk will be on Friday of next week at the usual time, and I will send out an announcement of that soon. Okay, then bye-bye. Have a nice weekend.
Bye-bye.